Yeah, hi. Today we're going to talk about Newton's three laws, and specifically, I'm going to highlight the difference, or rather, a common misconception between Newton's first law and Newton's second law. So I believe there's a common misconception, which is that Newton's first law is a consequence of the second law, and the reason why people might think so is because Newton's second law says that F equals ma, right? For at least for a constant mass. Um, and Newton's first law says that an object at rest will remain at rest, and an object in motion will remain in motion unless there's an unless there's an external force, right? So basically, Newton's first law is saying that F equals to 0 implies A is 0, right? If you have no net force acting on you, then your acceleration is 0, and your velocity is constant. And so people often see this expression and be like, isn't Newton's first law just substituting F equals to 0 into Newton's second law, right? And the answer is that um, this, this over here is actually not what Newton's first law is about. Newton's first law is actually the definition of an inertial reference frame. So we see that over here, one part that is constantly left out, right, in most textbooks, but it's actually over there, is that Newton's second law only holds an inertial reference frame, right? Um, and what is this inertial reference frame? The inertial reference frame is defined in the first law. So the first law says that the first law is basically saying in a set of all reference frames, right? There's so many reference frames, so many perspectives one can take. Be it whether you're in an accelerating bus or whether you are a muon traveling into the atmosphere at a constant velocity near the speed of light, or whether you're in a rotating reference frame. There's so many reference frames. Newton's first law picks out a subset of these and calls them inertial. Right? The rest will be, of course, called non-inertial. But Newton's first law says that this subset of these reference frames is what is inertial. And roughly speaking, inertial reference frames are those reference frames such that the velocity is, the velocity not zero, the velocity is constant. Right. So examples of inertial reference frames are a bus traveling at constant velocity. Examples of non-inertial reference frames are your rotating frames, right? If you're sitting in a carousel, you're in a non-inertial reference frame. If you're sitting in an accelerating bus, right, you're also in a non-inertial reference frame. So Newton's second law says that the total says that in an inertial reference frame, right, only in an inertial reference frame does the net physical forces acting on you equal the change in velocity, the change in momentum, right? And of course, if m is a constant function of time, then this is just ma. So I'd like to give you two examples where this, to make this clear, right? So in an inertial reference frame, the physical forces that are acting on you, right? The physical forces acting on you is it changes momentum as such. However, in a non-inertial reference frame, this does not hold. The physical forces does not equal change in momentum. And of course, this is a statement about inequality, and that's just useless, right? We want to find equality. We want to find equations that tell me exactly what things are equal to. So we actually have to modify in order for this to still hold. I actually have to modify Newton's second law for non-inertial reference frames to include something known as fictitious forces. And these fictitious forces are examples of fictitious forces are your centrifugal force or your Coriolis force. These are just two examples that appear when when you're in a rotating reference frame. So these are examples that appear when you're rotating reference frame, and we'll talk about this in future. So okay, so I said I wanted to talk about two examples. In this case, the two examples, the first example would be an accelerating bus. Right? If I was in a bus, and the bus accelerates off at some acceleration, non-zero acceleration, then I'm gonna feel like I'm being flung back to the back of the bus, right? I'm gonna feel something. I'm gonna feel like I'm just suddenly being thrown back to the back of the bus. But if I look around me, are there any forces that are acting on me horizontally? Right? No, there are no net forces. There are no physical forces that are acting on me horizontally. And and the reason why my momentum changed, even though there's no physical forces acting on me, is because I'm in a non-inertial reference frame. And in a non-inertial reference frame, there are fictitious forces due to the fact that your reference frame is accelerating. So that's just an example where linear acceleration causes a fictitious force, right? Causes a fictitious force to feel like you're being pushed to the back of a bus, even though there's no physical forces acting on you. The next example would be a carousel. So in a rotating carousel, you're sitting here on your seat, right? And you feel like you're being flung outwards, right? And the reason you feel like you're being flung outwards is because you're rotating at some omega, right? Some constant angular velocity, right? And when you're in a rotating reference frame, even though your speed doesn't change, right? But your velocity changes direction, right? Your velocity changes direction. And the thing that changes your velocity is the centripetal acceleration. Your centripetal acceleration is always pointing towards the center, and it's always changing your velocity such that your velocity will go round and round and round. And because you're actually experiencing an acceleration, right? If you're this guy on the carousel and you went into his perspective, from his perspective, because he's in a non-inertial reference frame, because he's rotating, right? He's gonna feel his momentum changing, even though he's gonna feel his momentum changing. Let's say there's nothing holding him in, right? He holds a ball in midair and he lets go. He'll see the ball move away from the center of rotation. He'll feel the ball move away. And the reason why he sees the ball move away, even though there's no horizontal physical force that acts on it, the reason is because there's a centrifugal force, which is a fictitious force, due to the fact that he's in a non-inertial reference frame. So I went through this in a video. If you search TCH survives centrifugal, I went through this in detail where I explained the difference between the centrifugal force and the centripetal force. But basically, the centrifugal force is a fictitious force due to you being in a rotating reference frame. So yeah, so that's the second law, and there's a bit of nuance behind why this word inertial is very important, right? And why the first law is even needed in the first place, because in order to define what this inertial means, we need to look for the first law. So in some sense, the first law, the reason why it's called the first law and it's not and it's not a subset of the second law is because the first law actually defines something that the second law needs. And that means that if you wanted to derive, since Newton's second law is actually only talking about inertial reference frames, right? If you wanted to derive what the fictitious forces look like, how do I know that centrifugal? How do I know that centrifugal force is m omega squared r? How do I know that that is true? The reason I know that is true is because in order to derive this fictitious forces, right, I need to first choose an inertial reference frame, and then I go from the non-inertial, I transform coordinates so that I go from the non-inertial reference frame to the inertial one. I apply Newton's second law in the inertial one, right? And then I go back into the non-inertial reference frame to see that, oh, it seems like I've picked up some additional terms which are called fictitious forces, right? But at the core, right, Newton's second law is a statement about inertial reference frames. It's just that we can derive what happens in a non-inertial reference frames by changing coordinates into inertial reference frames first, and then we're deriving the equations. I'll talk more about this in a future lesson on rotating reference frames, because there's a bit of math in order to derive the fictitious forces. Okay, so that's Newton's second law. So Newton's third law is simple. It's just talking about the interaction between two bodies, right? So whether your two bodies are whether the two bodies are interacting via gravitational force, electrostatic force, or contact force, right? And every action has an equal and opposite reaction. It's a common saying about it. Do note that the left-hand side is A on B, meaning that we're actually considering the force body diagram of B. So consider all the forces on B, and one of them is due to another object A, and that's what we call A on B, right? Whereas this one over here is B on A, meaning that we're actually considering the force body diagram of an object A, and there are many forces that act on it, and one of them is from B, so that's what we call B on A, right? So even though these two are equal, right, they're acting on different objects, right? It's just something to take note of. Question: does Newton's third law apply to all forces? And the surprising answer is no. You can read up online on whether the Lorentz force obeys Newton's third law. And you actually see that the answer is no, because the reason why the answer is no needs us to go a little bit into the field of Lagrangian mechanics. Because in Lagrangian mechanics, we'll see how we actually define momentum, right? It's known as a canonical momentum, right? So it turns out that if we write the Lagrangian for electromagnetism, right, which the Lagrangian for electromagnetism would give rise to the Lorentz force. If we write down the Lagrangian, the momentum actually looks something like P minus EA, right? So P minus EA squared, something like that. And because of this, right, momentum, there's some kind of exchange of, there's kind of the momentum of a particle, right? This is a particle. It's kind of intertwined with the momentum of the electromagnetic field. Right, A is the electric field, magnetic field packaged up into something called a vector potential, but it's a bit complicated. But roughly speaking, a particle will experience the particle's momentum is kind of, the definition of a particle's momentum is intertwined with the electromagnetic field's momentum in some sense, and because of that, right, the Lorentz force doesn't obey Newton's third law. Yeah, I'll talk more about this in another video, but just know that the Lorentz force doesn't doesn't obey Newton's third law, but most other forces should. I don't know of any other example, at least in undergraduate physics or physics Olympiad, where this doesn't hold true, where Newton's third law doesn't hold true. Yeah, so for most mechanics questions, it'll be fine. Anyway, for Lorentz force, most of the time we're not interested in conservation of momentum, so it's fine. Okay, so those are the three Newton's laws, and in the next video I'll talk about impulse, and in the following video I'll talk about work energy theorem.